Good morning, everyone. Thanks very much for inviting me down here. It's an honor to be here. Hopefully these slides will come up. All right, great. So I'm Aaron Lee. I'm from the University of Washington. I'm going to be talking about applications of AI from my lab in ophthalmology and vision science. These are my funding disclosures. I'm going to kind of give you an overview of our sort of journey through applying deep learning to various different ophthalmology problems. And I kind of want to start by, reinforcing this idea that we live in the era of machine learning. So every time you do anything with your phone or with your browser, machine learning algorithms are really driving the content that you see, the text suggests that come up when you try to text somebody. It's all driven by ML. And I think it's nice to start thinking about what can we do inside of ophthalmology and vision science to apply these technologies. It's also nice to kind of get some of the terminologies in order. So the field of AI is actually very broad. It encompasses a large family of different kinds of algorithms. And within there's a subfield called machine learning. And within that, there's a relatively new field called deep learning. And as you heard from the previous talk, which was beautifully done, these deep learning networks are really no different than the underlying technology that drove a traditional artificial neural network that you heard about back in the day. The difference was that these were relatively shallow. They only had about 1 to 3 fully connected layers. And in my opinion, there were sort of 4 kind of advances that make deep learning, what we call deep learning today, different from the traditional neural network. First, it was the availability of these graphics processing units. They realized that they could be used for something other than playing computer games. They were massively parallel linear algebra engines. The use of convolutional neural filters that were spatially aware, and nonlinear activation functions. So these last 2 things are not new. They've been around for a long time, but it was the incorporation of them with the graphics processing units and enough data to train these neural networks that allowed us to live in this kind of exciting world today where we can train very large neural networks and as you add more and more data, the performance of these neural networks increase. I think it's also really nice to talk about the terminology of the problems. In machine learning broadly, there's 2 different types of problems. There's supervised learning problems, and then there's unsupervised learning problems. And in supervised learning, we know exactly what the right answer should be. And most problems in medicine and biomedical imaging, we know what the right answer should be. So they all sort of fall underneath supervised learning problems. So an example of that is given a picture like this, tell me what object is in it, and that would be a problem of classification. Slightly harder would be what we just saw in the previous talk with the localization of the polyps. That would be a classification plus localization. Can you tell me what's in this picture and where it is? Even harder would be an arbitrary number of different objects and identifying all the objects and being able to tell what they are. And the hardest would be to classify every single pixel in the image and provide a precise segmentation of the different objects in the picture. Unsupervised learning is when we don't necessarily know what the right answer should be. And it's actually kind of hard to think about problems that fit in this space. But this is one of my favorite examples. So this was a neural network that was asked to learn the latent mapping between horses and zebras. If you think about it, there's no pair of pictures out there in the world where a horse and a zebra are standing in exactly the same place and you can swap between them and train a neural network. Here it was given a stack of pictures that says these are all horses and these are all zebras. And can you learn to transform in between these 2 different kinds of pictures? And what's kind of neat to see is that not only is it painting the stripes on the horse, but it's also changing the color of the grass because it learned the context at which zebras exist. It's different than the context where horses exist. Another example is what was alluded to before. A company called DeepMind in London built a deep learning network based on reinforcement learning that was able to beat the world champion at Go. If there are people in the room who are more from a traditional statistical background, I love this table and I show it a lot because I think it's really helpful. These concepts in ML are not necessarily new. They're equivalent to what happens in statistics. So a network or a graph is really the same thing as a model. Weights are the same thing as a parameter. Learning is the same thing as fitting a model. Generalization is the same thing as a test set performance. Supervised learning, statistics, they would call those, more specifically regression or classification. Unsupervised learning in statistics, they would have called clustering or density estimation. But my favorite part of this table is this slide. So the last point I kind of want to make is that these neural networks, these convolutional filters and deep learning architectures in general were sort of modeled after the way that the visual cortex and the retina processes visual information. So I think applying them to ophthalmology problems is something a little bit poetically recursive. So I kind of like that about these problems. So you're going to move on. I'm going to start by talking about our very first project that we did using deep learning. And one of the things that I did when I first got to the University of Washington was I started trying to engineer ways to collect massive amounts of data. So I found a way to take all the data in our electronic medical record and extract them and anonymize them and then link them to all the imaging data that we were capturing so that we can build large labeled data sets. So this is, what I kind of loosely call the OCT EMR database, and we have about 5.5 million OCT images, 90,000 macular volumes, 16,000 patients, more than 10 years of time, all scanned with exactly the same imaging protocol. And because we linked it through the EMR, we know their visual acuities, their diagnoses, what interventions they had, and the expert interpretation. And so by building this kind of labeled data set, we can start to apply these concepts from deep learning. And the easiest problem that I could think of was, can deep learning learn to distinguish between OCTs of normal retinas versus AMD retinas? And so we extracted the data set, and it's about 100,000 OCT images from our data set. And we used a well-known architecture called VGG16 to train this model. And it's basically a binary classification, yes or no kind of model. And during training, what happens is that it's fed an OCT image, and the model gives some sort of prediction. It guesses, I think this might be AMD, and we tell it what it actually is. And it does this process called backpropagation, where it minimizes the error and learns. And so the next time it sees a different kind of image, it guesses AMD and says, yes, it's actually AMD. And then we reinforce that positively. And by doing this over and over and over millions of times, we can build a network that can achieve these kinds of performance. So we achieved very, very good ROCs and very good sensitivities and specificities. And when I first got these results, I felt nervous about publishing them because I didn't know what was going on. I didn't know if it had learned some systematic noise that was different between these two different image sets. And that kind of gets to this heart of the black box, right? We don't know what's going on inside. And so I was really frustrated with this problem. So the largest part, the time it took to train the neural network was very short, but the time that we took to kind of build these explainability or visualizations was much longer. And what we eventually settled upon was actually a very simple concept. So this is something that we took from the computer vision literature. And it's this idea that if I asked you, is there a ball in this picture? You would say, yes, 100%, I am certain that there is a ball in this picture. But then if I occlude a part of the picture, and I ask you, is there a ball, you'd still say yes. And if I systematically move the box around to every single position on the picture, eventually this box ends up here, and I'll ask you, is there a ball in this picture? And you say, I'm not sure anymore. That's what we did. So we took the model that had been trained already, we fed it a new image, and we systematically included every possible position, and we looked to see what happened to the confidence that the model had saying that this was AMD. And by doing that, we could generate these kinds of heat maps. And the heat maps made me feel much better about publishing this result because it kind of gave an insight into what the model was looking at in order to make the determination that this was macular degeneration. And what's neat about this generic sort of model is that we can train deep learning classifiers to teach us subtle differences between different image sets. So that was sort of our very first foray into deep learning. Our next foray was to do feature segmentation. And the problem that we turned to was segmenting intraretinal fluid. So as everyone knows, intraretinal fluid is a big problem caused by lots of different diseases. Full volumetric segmentation would be really useful for clinical outcomes. But manual tracing is really time consuming and costly. So I think one of my students is trying to trace all the intraretinal fluid cysts there, and it's taking forever. I think it's sped up 5 times too. So, and what we did generically is we said, okay, this is the problem we want you to learn. We're going to give you an OCT. We're going to put it through the model. And what I want you to give back to me is the binary segmentation mask where all the intraretinal fluids are located. And after 1 week of computation, about 200,000 iterations, we achieved a max validation DICE score of 0.91. And if you know anything about DICE coefficients, that's actually very, very good. But seeing is believing, right? So here are some examples. On the left is the original OCT image that were not in the training set. On the right are the color-coded confidence of the model calling that intraretinal fluid. And here are 2 more examples. And when I first got this result and I started showing people who had been working in this field, and they said, oh, you know, intraretinal fluid is really not that hard of a problem. All you got to do is find the ILM, which is pretty easy. All you got to do is find the RPE, which is pretty easy. And anything that's dark in between those 2 layers, that's intraretinal fluid. So it's really not that impressive that your neural network can do this. But if you follow that heuristic, you would incorrectly label all the shadows underneath the vessels as intraretinal fluid. And what's kind of impressive is that the network learned not to do that. So we wrote that all up and we published that, and unfortunately, you know, the coolest, like very often the coolest parts are not in the papers, right? So this is something that we really found kind of mind-boggling. So what we did here is we really slowed down the learning rate. So we slowed down the way that we wanted to watch the network learn to do this task, and we wanted to see how it learned to do it. So we slowed down the learning rate a lot, and we started training it, and at every iteration we fed it new images that it's never seen before and see what kind of error it makes. So if you look up here, you know, this is a shadow underneath the vessel, and I'm going to play this movie, and I want you to see what happens. At the very beginning, it makes this mistake. It calls this intraretinal fluid, but it learns very quickly that it's not. And then down here, it says this pocket of subretinal fluid is intraretinal fluid. But over time, as it gets fed more and more examples, it learns that it's not. And so you can watch it learn to do this task. But the coolest part about this video is something that you might have missed right at the very beginning. So this was a little bit hair-raising for me because when we first slowed down this movie, we saw this. So here, the network learned to find the ILM and the ISOS junction without us teaching it to do so. It emergently kind of learned that in order to solve this problem of finding the intraretinal fluid cysts, it had to solve this other problem along the way. And that's kind of crazy because we literally just fed it where the intraretinal fluid cysts were. And this is very similar to the way that I teach residents of how to find intraretinal fluid, is to identify the anatomic borders. And it had learned to do that emergently without us teaching it to do it on the way. Another area that we did some feature segmentation work in is in the field of OIR, so oxygen-induced retinopathy. It's a commonly used animal model to study angiogenesis. We noticed that a lot of people who are doing it are the people who are not blinded to the experimental condition when they're doing the segmentation, so there might be some bias there. And if you ask the same person to segment later, they're not necessarily internally consistent. So what I mean by that is if right now what happens is a lot of people take this kind of image into Photoshop and they try to generate this kind of segmentation mask. And what they're looking for is to quantify all the neovascular tufts as well as the vaso obliteration region. And this is a model for ROP. So what happened is we collaborated with Marty Friedlander, who lives not too far from here, who had about 10 years of continuous basic science experiments that powered about 5 PhDs and countless medical students who were doing this task. And so he had about 1,000 of these images lying around. And when we looked in the literature, we found that there were some semi-automated methods. And when we asked them, why aren't you using these things? They said, well, they're actually not very automated at all. And what we ended up doing was building a pipeline where we had broken down the problem into several discrete steps, and we trained each one using AI. So we trained the segmentation of the vasoobliteration region as one problem, the segmentation of the neovascular complexes as another problem, and the segmentation of the retina. And we built a pipeline to kind of handle these problems. And so here are the results again. So in the first column, you're seeing the input, the raw image. And then in the middle, you're seeing the human expert segmentation. And on the right, you're seeing the deep learning segmentation. And here's the same thing for the neovascular tufts. And I think in particular, the neovascular tufts, the network did a fantastic job of identifying these things. So we again published this, but we took this a little bit further. So we actually open sourced all of our code and the model weights and the model parameters and everything. And we even deployed a website because we recognize that researchers who are out there are not the most computer savvy and don't have GPUs lying around to do this work. So we built a website that could actually do this task. Oh, sorry. So I'm demoing the website here, and what we're doing is we're uploading these different images to the website. And what's kind of neat about this is that these images are from totally different labs from all around the world. They were not part of Marty Friedlander's lab or other labs. These were labs that were had started to use this website. And so you can see that already the images sort of look very different than the images I had shown you in the previous slide. I'm just going to skip ahead here in the interest of time. And so what happens is that it's actually launching in the cloud. We engineered a pathway for it to launch multiple computers when these images come in to process them in parallel and provide the segmentations back down to the researcher in a totally transparent and fully automated way. And if you watch here, you'll start to see the VO ratio and the NV ratio pop up, and the researcher can then go and download the segmentation masks and take a look at them and verify that they actually look correct. So this is really neat because we're allowing researchers who used to spend hours and hours doing this segmentation task in Photoshop to actually think about designing their experiments and think about the next kind of experiment they're going to design rather than sitting there doing this sort of mind-numbing, boring task. And after we launched the website, we've processed about 2,000 images around the world. And we haven't stopped there. So the next model that we're tackling is the DLR knockout mice model for retinal neovascularization. And we've already made a substantial amount of work, and we want to integrate this into the website to allow researchers working on these mice models to also access deep learning. So I think it's safe to say that we're actively trying to accelerate biomedical discovery and vision science using deep learning. The part that I am most excited about, and the area that we spend most amount of time doing research in, is this idea of image-to-image generation. And I'm going to switch gears a little bit and talk about glaucoma. Everyone knows glaucoma is a big deal. And this was in collaboration with Dr. Wen and Chen at UW. And right now, people get these Humphrey visual field measurements done, and it generates this perimetry report. And that's how we monitor disease progression in glaucoma patients. So what we did is we created another big data pile. We went and we took all the visual fields that were done, and we built an automated pipeline to extract the perimetry points out from the Humphrey visual field files. And so that translated to about 32,000 24-2s of 8,000 patients over 20 years of clinical practice, and about 1.7 million perimetry points extracted to the 100th decibel. And the goal, the machine learning problem that we phrased was to take a single visual field and try to predict what that visual field would look like in the future, just from a single visual field. And so we're worried about, overfitting and all these different kinds of machine learning problems. And so we took a very sort of stringent approach where we immediately divided the visual fields by the patient level, and 20% we reserved them for testing. So we only tested it once at the very end. The other 80% we did tenfold cross-validation, and we did model selection, and we picked hyperparameters and built the models. And at the very end, we tested on that test set once. And so all the things I'm going to show you after this slide are from that test set. So the model had never seen it before. And what was kind of remarkable to see was that the model could actually predict what that visual field was going to look like up to about 5 years into the future. All it had as input was the current visual field and the age and gender of that patient and nothing else. So, one of the things that we used as sort of a negative control were neurologic fields. We wanted to make sure that the network did not predict that those were going to progress. And it's nice to see that it doesn't predict, it doesn't get confused in thinking that that's a neurologic field with a glaucoma field. What's really remarkable is to kind of see how well it does in different severities of glaucoma at different time points. So here, what you're seeing is on the left-hand side is the current visual field. The middle is what actually happened at that time interval later, and on the right-hand side is the AI prediction. What's also kind of neat is that we can do serial prediction. So given a single visual field, we can predict at different time steps into the future, and we can compare them to the actual visual field at those time intervals into the future. And we can see the model does a fairly good job of predicting the progression of the visual field across time. And so how is this possible, right? Because a lot of glaucoma specialists probably in the room are balking at this because they're always taught that you need 3 visual fields at baseline to understand where the patient's at, and et cetera, et cetera. Well, what happened is that the model learned by watching that other 80% age. They watched the progression of that, and it learned within the trainable parameters. It learned the patterns that predicted progression. And so we achieved the overall MAE of 2.47, and I think this is the baseline. So this is, this marks sort of where we are given such few information. But the future work would be to include some very obvious parameters, like the current IOP and any kind of surgical intervention that occurred, and eventually end up in a situation where you're sitting in clinic and you have a visual field. And you want to know whether you should do glaucoma like a trab versus a tube or add another drop. And we can feed them into these networks, and we can switch on these different parameters. We can see what would happen to the predicted field in the future. Another image-to-image area that we're really excited about actually came accidentally. So I remember these papers before OCTA existed. They were going to hand draw all the vessels on the OCTB scan, and if you do that for a really dense OCT scan, you could take that en face and make it look like an OCTA before OCTA existed. So I wanted to do that. I was going to get an army of medical students to go and circle all these dots. But then I remembered I was at the University of Washington, and we have Ricky Wang there, who is sort of the father of OCTA in many ways. And he has a very large data set where he has the exact structural OCT scan and the corresponding OCTA-B scan. And what we did is we took the structural OCT and put that as the input of the neural network model, and we tried to predict what the OCTA would look like. And so after 2 weeks of training, we were able to do this. So here, what I'm showing in the left-hand panel is the original structural OCT-B scan. In the middle is the OMAG OCTA-B scan. On the right-hand side is the deep learning prediction. And what's kind of remarkable about this is that the red arrows point out vessels that I can very easily see as a retina specialist. But the yellow ones are ones that I'm not sure I can make out in the structural B scan, no matter how much time I try to have. And what's kind of nice about this is that this is a deep learning problem where if you think about it, we've kind of cut out the human in generating the truth here. we've relied on another physical measurement to set the ground truth, and we wanted to push the limits of how far we could train deep learning, where we had sort of an undeniable ground truth to train it with. And so after doing an on-FOSS projection, you can get an image like this. And I just want to emphasize, again, this is not OCTA. This is from just simple structural B scans that we could run this deep learning model and turn into what looks like an OCTA. And so what about diseases the AI has never seen before? We used that as sort of a test set. And it's actually quite remarkable how well the deep learning network is able to do. If you kind of look and zoom in on the insets, it's amazing how much detail it's able to pull out from a conventional OCT scan. And so here's another set of examples from retinal vein occlusions. And what's neat about this is that there's lots of data out there that have OCT, but doesn't have OCTA because it didn't exist. We can kind of use this technology to go back in time and extract sort of vascular factors. The other thing that's kind of neat about this is that it's predicting flow from structure. It's kind of like I give you this picture and I ask you, how fast is this car moving? Or I give you these pictures of water and I ask you, can you give me the velocity, the speed at which the water is moving? And that's what deep learning is doing, is looking at the structural B scan and predicting at each single A scan position, what is the speed at that position. And we had this hypothesis that it's really relying on high frequency spatial speckle information to make this prediction. So what we did is we systematically blurred the OCT B scan over time, and we watched to see what happened to the fidelity compared to the actual OCTA. And we showed that, yes, there is a very nice relationship between the amount of blurring and how well it can predict. So again, it allows us to analyze past OCT data, and hopefully in the future, it would allow us to accelerate and enhance OCTA acquisition. We've taken this a step further, and we actually applied it outside of ophthalmology to neuroimaging. We looked at being able to predict things like MRA from MRI, and DTI from MRI. And the underlying sort of hypothesis that drives us today is that there are sort of unseen spatial features that are present in conventional imaging that may be indicative of function. So by using reconstruction to DTI, we can actually recreate the pathways of the way that the brain is connected. And what's kind of neat here is that the right-hand side is generated from conventional T1 imaging. It's not from DTI, diffusion tensor imaging. So I go around to conferences and people ask me, like, this is really cool stuff. How do you do all this work? What kind of computers do you need? What I did is I built a GPU cluster for my lab. And right now, well, as of June of last year, we were sitting at just under half a petaflop of computing power just for ourselves. And teraflops probably doesn't mean very much to you, but the fastest computer in 2000 was 7.2 teraflops. 2004 was 136, 2005 280, and in 2007, not that long ago, the fastest computer on Earth was about 478 teraflops, and that's about where we're sitting right now to do this computational work. So in summary, I think deep learning and AI, it's a transformative technology. It's going to change the way that we do things. And what some of the really cool stuff is, like, some of the emergent behavior that the network is able to do. And this idea that there might be latent data associations that we've been missing this whole time is also really fascinating. And none of this work would be possible without the team that I have. So I just want to thank all the members of my lab and my funding sources. Thank you. I think that this is as good as what this result represents is how well the model can predict without having those kinds of information. What will be truly interesting to test that question is to add that information in as auxiliary inputs into the model And if it drastically improves the ability of the model to predict, that would support the hypothesis that that knowing what drugs and what surgeries the patient has is helpful in understanding the progression of the disease. If the null hypothesis is true, then everybody is going to have a different discussion. Yeah, so that's a great question. And you're not the first to ask that question because there's already been a lot of work that's been done on this. So there's a pretty famous paper that came out of the Stanford group where they were trying to answer that specific question. And there's actually two separate problems, right? So given an image, can you predict the neuronal activity of the retinal ganglion cells? Or the vice versa problem. Given the neuronal activity of the ganglion cells, can you predict what the image was? So it's actually sort of two separate problems that are definitely interlinked, but they are actually two separate problems. So there's a lot of work that's being done right now to curate the data set so that we can build these models to try and do exactly that. Yeah, we tried 10 years, it didn't work. That's why we cut it off at 5. But I think even 5 years is still pretty amazing that it's able to do this. And your point is very well taken. Again, what was nice to see is that we saw sort of a dose-dependent response curve. So like the more time went out further, the more inaccurate the model was, which is what we would kind of expect to see. And so again, this sort of sets the baseline, right? So if we know this sets the benchmark for future work in this field where we can start to add these things and see how much of a difference it makes. If your hypothesis is true, then at 1 and 2 years, there wouldn't make a big difference. But at 5+ years, adding those covariates could drastically improve the model performance. What I meant by it had watched the other 80% is that the other 80% of that cohort, it had undergone the standard of care of glaucoma therapy at University of Washington, and it had watched what had happened to those patients as they were being treated by the standard of care. This is not an RCT, right? We did not do that. So thank you for bringing that up.
All right, thanks again, Aaron. That was great.